I am very excited to welcome our speaker for today. That is Ignacio Arganda-Carreras. He is an Basque Research Associate at the Computer Science and Artificial Intelligence Department at the University of Basque Country. His research focuses on biomedical image processing and computer vision, and his previous work experience has taken him pretty much across the globe, including Madrid, Berkeley, Prague, Zurich, Cambridge, Massachusetts, Paris, and now in Basque Country. So yeah, and during all his travel and going across the world to work on very interesting topics, he has developed a battery of methods for bioimage analysis, image processing, and computer vision using machine learning and other methods. So today he's going to talk to us about BiaPy, which is a ready-to-use library for bioimage analysis workflows. Again, very important topic. So we are very excited to hearing from you, Ignacio. So please take it away.
Thanks so much. Thanks, Aastha, for the very nice introduction. And thanks all the organizers for giving me the opportunity to be here today. It's a real pleasure and to actually be introducing what has been the work, I would say, about the last couple of years of my lab, or an important part of the work of my lab, which is what we call BiaPy, this library to create bioimage analysis workflows that I hope in this community will be found very useful. So what I thought for the talk is to divide it in two parts. In the first part, I will tell you how this whole thing started, how is it going, the current state of things in the library, what you can do and you cannot do, which is also important. And also because I think it's a very recurrent problem for all of us, I would focus on one of the workflows that is interesting, which is 2D or 3D instant segmentation of any kind of microscopy images. So for that, I will go through the usual approaches, what we usually use as problem representations to solve this kind of problems, and what we propose in our library to hopefully have a generic solutions to it. So this should be about 50 minutes. And then what we commented before, we have later this questions and answers period for 10 minutes. But if at any point you have any question, please feel free to interrupt me. So this could be more interactive if you want. Okay. So first things first, how this whole thing started. It actually did thanks to this guy here, Danny, who's was at the time my master student in 2019. He came to me. He was a computer science student, and he wanted to jump into biomedical image processing, deep learning, what else? And then co-supervise with Arate. We proposed him to do quite initial project to start learning how to do developing in Keras and TensorFlow. And we proposed him to implement a bunch of state-of-the-art models to segment mitochondrial and electron microscopy images. So for that, we took 3 public databases, not very large, and 1 database that we had from some collaborators. And it went well. It went actually very well. So he became my PhD student, and Arate's as well. And a few years later, not because it took us 2 years, but because you know how the publication system works, we got a very nice paper in neuroinformatics with what I think is a very honest comparison of the state-of-the-art methods to do semantic segmentation on this type of data, both in 2D and 3D. He actually did intense implementations of previously published networks, because no surprise there, but many of them, they come without the code. And then we did something else. We also tried to not only reproduce the results that were there, but also check if they were consistently providing the same results, meaning that if we take the whole, let's say, workflow, and we repeat the experiment with the same parameters, we were expecting to have always more or less the same good results. And again, no surprise, well, it wasn't always the case. So we actually ended up founding our own models that were what we call stable or robust, because they provide us with consistently good results, at least on these public benchmark data sets. So by the end of this project, we had open source code because we made it public with our publication to, of course, well, they were implementing tons of state-of-the-art deep neural networks for semantic segmentation in both 2D and 3D. And we built what we call robust training configurations, meaning that we have always very consistently the same results. So it was all very reproducible. And we have a bunch of methods to, of course, load the data, partition the data. We have data augmentation methods that were specific for the microscopy modalities that we were using. And of course, a bunch of evaluation metrics to quantify and properly compare the different results. And very importantly, when this is something that in publications, usually they don't give enough importance to it, is that how we post-process the data, no? Because out of the neural networks, we usually have some raw results, and sometimes we have to, if we have done patches, we have to create again the full image, and the way you do the mosaic is actually having a big impact in the result. You can do test time data augmentation, which also improves the result, but it should be specified. And so when we do this, we did it with the full pipeline for all the methods under the same conditions. So in other words, we ended up with something looking like a Python library for semantic segmentation workflows. It's actually looked more like a bunch of different scripts that we kept reusing. And given the success of these approaches, with some collaborators from Harvard University in 2020, we actually released 2 big data sets, completely labeled for mitochondrial segmentation. As you see here, they are colored, so this means that we are actually going into instant segmentation. Every object has a different ID, a different color. And we have these 2 big volumes, one from rat tissue, one from human tissue, that we call Me2EM. And we also created a challenge that we recently published the results from at ISB in 2021. So suddenly we had to create new models based on the code that we had before, new data augmentation. Now everything was 3D. We had other challenges there, different post-processing, of course, because from the for every object, we need to get the individual instances, and therefore we needed different metrics. And very importantly, we had to deal with a much larger scale data set. So suddenly, from our more or less well-organized set of scripts, we ended up with a chaos of a script, not only in Python, but in other languages also to run in a data center, etc. So at some point, I talked to my student, Danny, and I said, okay, we have to think clearly on how to do this in the future, because probably we want to reduce it and we would like to have something more like a library, right? So passing from a bunch of scripts to something that is easy to install, not only for us, but for our collaborators, that we can easily develop, but also maintain, and for other people to contribute to, because you know how it is. If the student leaves and suddenly everything is a mess, then the whole project dies. And I think this was quite interesting to maintain. Also, we wanted to focus on reusability, because we kept having more and more projects. And what we were doing until that moment was to take the old scripts, change a few paths and parameters, and then run them again. No? So we wanted to stop doing this, to not create new code for every new project that we had. And of course, we wanted to open the range of workflows that we have so far, not only segmentation, both semantic and instant segmentation, but to start doing with the same infrastructure, because loading the data, post-processing the data is very similar, other typical bioimage analysis tasks, including image segmentation, super resolution, object detection, but as you see here, based on center point detections in both in 2D and 3D, and denoising. And the most important thing out of the whole identified needs for a library is that we need to find a proper name. Okay, because so far I think this whole thing was called EM segmentation in Danny's GitHub. So that's how BiaPy was born. What we call it BiaPy, it stands for bioimage analysis pipelines. Okay, turns out that there was some small projects also called BiaPy in GitHub, but you look for it, this is the biggest one. And this year we made a small conference paper for ISBE to present it to the community and get feedback. So how does it work? Well, the whole I would say focus of BiaPy is, as its name indicates, is the workflow, right? Meaning, what do we understand by a workflow? Well, actually, we have three main components. Always at its core, we have a deep learning model. Of course, now it's the trend, right? But it's also the state of the art. And then we have a pre-processing module and a post-processing step. As input, of course, we have images of any modality, size, number of channels, etc. But we could also have images containing their labels, for example, for segmentations, or some annotation files, for example, in the form of a CSV file with detection, classes for classification, etc. And the output, well, it could be an image, not always, of course, or an annotation file where we have maybe the positions of the predicted detections or the classified the categories that the whole pipeline predicts, etc. So what do we have in pre-processing? Well, here we have many methods that I mentioned before that we were using, for example, to take the big images and then do patches in 2D or 3D, to normalize the input data to the workflow, to change the problem representation, because sometimes we have to pre-process a little bit the data so the life of the deep learning model is easier later, and some filtering as well. And post-processing, as I said, there's a lot of things that we can do. Here, actually, the analysis is also performed in some cases. We have post-processing filtering, but also, very importantly, how do we do the mosaic of the different patches out of the input patches, or we have agglomeration methods, non-maximum suppression methods for detections or segmentations that are nearby, etc. And plenty of evaluation metrics, and we spent a lot of time on that to, of course, because we are focused on the computer science aspect of this, to really quantify our results. So, in my opinion, what we have is some advantages for users in the sense that for them, it's easy to combine methods on the pre-processing or post-processing step with these different deep learning models. We see how, and the only thing that they need to worry about is to put their data in some folders more or less organized, so the input to the whole workflow is clear. And for developers, I also think it's nice to have it like this, because we have people that maybe they want to contribute because they are deep learning hardcore developers and they want to contribute with just a new model for segmentation or for detection, etc. Or we have more people related to generally image processing, and they want to do some general pre-processing step or some analysis, and then all the analysis can be included in the post-processing part. So how do we configure one workflow in BiaPy? Well, it's actually just, if we go to the hardest, but also the raw data, it could be to just edit one text file. Okay, it's called a YAML file. It's a configuration file that looks exactly like this. It has some keywords that we have here in blue, and then the values of those fields in black. Okay, so here what we do is we define the different steps of the pre-processing module, the deep learning training and inference, and the post-processing module. Okay, so for example, we say, okay, we have a workflow that is a semantic segmentation workflow in 2D. We want to use patches of this size. Here are the data, in this path, with other path. We do some partitioning, etc. And then we have ways through the keywords of defining the deep learning architecture, the optimizer that we're going to use, etc. And then at the end, we usually put in the test tag all the analysis and post-processing operations. Okay. So ideally, what we are providing is for every type of task or problem, because of course, if you don't know the keywords that you're lost, we provide a template, no? A already working template where you can just adapt to your paths or the size of your data, etc. So for every 2D and 3D type of problem, we provide one YAML file with this information. This is at the, I would say, the lowest level. Okay. So this has some advantages. It's very easy to prototype. You don't need to code. So you just edit here your paths or the type of problem, and that's it. But of course, you may think, yeah, but, I don't know the keywords in that. What are we going to do here? Yeah, that's true. We have a long list of keywords that unless you go to our configuration file and check them all, they're tough to know. Or otherwise, you're limited to those that are available in the template. So at this point, we didn't have a GUI. So editing this was, well, for me, useful, but I understand for non-experienced users could be very tough. So how do we install and run BiaPy? So here is where we decided that we wanted to actually target everybody in the field, from the non-expert user to the most expert users, for people that are very comfortable working in the terminal, cloning our GitHub repository, doing contributions, and then running things in the terminal just by editing that YAML file and maybe launching everything in a cluster. But then we also have everything installed with the dependencies in containers, in Docker and Singularity. And also for people who are not that familiar with that type of installation, when we have notebooks that follow the successful zero-cost deep learning for microscopy philosophy, where there's no code, you just have to edit different menus, right? And we can also run them in Google Colab with real data. Of course, depending on your data, this may not be ideal. You have very large data, you may have to jump into a local installation. So what kind of pipelines, what kind of workflows we have already implemented? Well, of course, I said at the beginning, we have segmentation workflows, both for instance and semantic segmentation in 2D and 3D for all kind of data. We always put these examples, but we've been working and collaborating with people doing fluorescent microscopy, rainbow images. We have plenty of different image modalities and templates. And these are the most developed because we started with them. But then we have also an ongoing collaboration for doing detection in 3D, as I said, just with point detections at the 3D center of cells, for example. This works very well. We have a student working on super resolution methods to increase the resolution of an image for a factor of 2 or 4 or 8. Okay. And then we have something experimental where we try to do self-supervised learning, where the target is not to obtain a new detection, a new segmentation, a new analysis, but to pre-train a model in a way that later can be reused for any other task with that similar data, and it has to be trained much easier. Okay. And out of completeness, we have also denoising and classification workflow. So in summary, what we have for every pipeline, we have is 2D and 3D templates. Okay, so 2D and 3D files, YAML files, will have full configurations that work out of the box with full documentation. By the way, I put the link here, but I will send you the link to the presentation later because I realize otherwise it doesn't make sense. I'll put it in the chat. And then for all these pipelines, we have notebooks that are runnable locally, are in Google Colab with real data. So we already provide some data samples, public data that you can run and check all the pipelines. And in some specific cases, because we've been using this for a while now, we have full tutorials that describe exactly what we did in some papers, adapting most of the time some of these pipelines with specific analysis at the end that reproduce our latest publications. Right? So now we use this for everything, basically. I also wanted to emphasize that we have this in the library, this set of methods that are for data augmentation, but specific of microscopy images, for fluorescence, color images. We have also adapted, for example, popular data augmentation methods to 3D, to do, for example, cutout, grid mask, etc. And also, when we work with tissues, it's also interesting to simulate things that usually occur in the sectioning process. So we have misalignments, missing sections, etc. So this kind of data augmentation allows us to train the models in a faster way with smaller data sets. So latest news, we have a logo, which is this boat here bringing the microscope, hopefully somewhere nice. You have to tell me. And then we have a Wii. Okay, so in our Wii, in the graphical user interface, it checks first you have a Docker installation and you have GPUs in order to use it. Otherwise, it goes in CPU. And then there's three options. You can either create a new workflow, and then it brings you to all the pipelines, so you can have a look at them and see the details. For example, if I select instance segmentation, I get the description of the workflow with some links to datasets and the templates as well. Okay, and if I select it, then I can go configure with different menus on the background that YAML file. If I can select where my images are, what kind of model I'm going to use, what kind of post-processing, and all the hyperparameters of the model, etc. Depending on the degree of expertise that you have, then you can select more or less options. You can also simply load and modify an existing template, okay, just to put your path, or directly, if I pass you, for example, a YAML file, you can click on run workflow, and then out of the box, it will run locally in your machine. Okay. Okay, so that for the first part of the talk. About the second one, because as I said, this is something that I guess we all face when we work with microscopy images. I thought it could be interesting to go into more detail for a typical workflow, such as the 2D or 3D instance segmentation. Yeah.
Maybe Ignacio, since you wanted to take some of the questions right in the middle, I see there's one in the chat since it's the middle of your talk. Maybe, do you want to ask your question? If not, we can read it out. So Raul asks, are the models based on existing... sure, go ahead.
Okay, excuse me. I just want to know if all the models based on existing pre-trained model like Stargis 3D or CellPose, like you stated earlier, and also if we always need masks to use the BiaPy.
You always use
masks, labels, I mean.
Yeah, okay. Yes. So
thank you.
So no and yes. So far we are not using pre-trained models. I mean, you could do it, because one of the options in this is to load your own weights. Okay, so you take a typical network, you can load the models as well. And yes, so far in most of the pipelines we need labels. Okay, so we have the self-supervised pipeline that creates its own labels, and also for super resolution we also have ways of simulating low resolution images from high resolution images, but in general labels are needed. Yes. Rafa, you have a question too?
Yeah, so something a little bit practical. So I'm wondering, have you tried your pipeline with the new file formats like the SAR formats and so on, in such a way that, for example, if I have a model and I want to apply it to a humongous, SAR file, that it helps me with all the, smart tiling and putting things together? Because this is really, it takes a lot of time to fix this kind of carpentry, and it would be so great if you know, if something could help.
Exactly. So this is something that we have just done. You go to GitHub, one of the latest commits, because we had this collaboration to do detection on full brain images. And of course, we needed something like this. So yes, we are importing SAR files and then loading just pieces of them through H5. But yeah, we are there now. Yes.
All right, that's great. I will play with it.
Perfect.
Thank you.
Thank you. Okay.
All right, thank you. Yeah, I guess you can continue. There's no more questions I see in the chat.
Perfect. So thank you very much. So yeah, regarding instance segmentation, this is something typical for us, also in computer vision in general. And there are usually two kinds of approaches. One that we call top-down, because we take top-down in general is when you take a big problem and then you divide it, you break it into smaller ones, and then you solve the whole thing, right? So this is, for example, the case with the mask RCNN, which is it was already published in 2017, where the big problem with multiple object segmentation actually does detection and segmentation. It classifies every object and gives you the masks. And then they build this monstrous architecture where you introduce the image through usually what we call the backbone network. It's usually a CNN. And then you have a smaller problems that you solve inside the network. You do, for example, region proposal. You select if the specific regions there is an object or not. Then you decide which is the bounding box of that object, and then you decide the category and the mask. So you have a very big network that does everything for you. This is what we call a top-down approach. So for bioimage analysis, we could do that. If we take an image, this is actually one image from one of the public data sets. So it's a typical one from FIPSEM, from mitochondrial segmentation. And then if everything goes fine, then you have all the mask and all the bounding boxes of your mitochondria. What's the problem here? Well, as Rafa said, typically in bioimage analysis, we have much larger images than just the 1024 by 768. Now, this is one of the volumes from our MitoEM dataset, and this is an actual comparison with this other dataset that we have here. And this size, of course, we cannot put it inside the backbone network here. Okay, so what do we do if it doesn't fit into the backbone network of our top-down approach? Or to say, well, Ignacio, this is a typical thing too. We do divide and conquer. We create patches out of the entire thing of a specific size, hopefully of the same size as the input to the backbone network, and then solve the whole thing. The problem is that, and this happens as well in this data set, many instances, many mitochondria in this case, go through many different patches. We have, this is actual data from this data set, where we have these are all the small mitochondria that we have there, but we also have very large ones going for thousands of boxes. So of course, you can get perfect segmentations in all your patches, but then you have to select somehow how you're gonna connect the instances that are in between patches through many, many different sections, which could eventually propagate a lot of errors. So because of this kind of things, in bioimage analysis, we usually opt for the alternative option, which is the bottom-up approach, which sounds very similar, but it's not. It's to focus first on solving the smaller problems and then integrate them into a complete solution. So you don't do a big network, but you do attack different problems and then merge them back together. Now, let's see an example. Again, with our image from the previous data set, we could say, okay, my small problem number one could be to calculate the object probabilities of my objects of interest, in this case, mitochondria. And we have something like this, we have a very nice prediction. And my small problem number two would be to, out of these individual probabilities, extract every instance. So we have this colorful representation of the instances. So we need to design a whole workflow. Well, in this case, let's imagine that we're just using images of this size to first identify the pixels or voxels belonging to the objects and then extract the instances in a second step. So for object probabilities, well, we know the state of the art is usually semantic segmentation network. And for instance, extraction we'll see later. So for which networks should we use? Well, in general, we all go for the most well, popular ones, no? But I usually tend to try first with the unit-like architecture. You probably know, but otherwise I'll go through the description of it. So the unit-like architecture is this nice network that was already published in 2015 that has this characteristic U shape, because we have first what we call the encoding part. Okay, so we have the image goes into the network and it suffers some convolutional layers, downsampling, convolutional layers, and more downsampling. So at every step it goes reducing its size. No, we have feature maps that are smaller until a place that all the information, let's say, is very condensed. It's called the bottleneck. And then we start to go up, no? Up, more convolutions, up, more convolutions, until usually now we recover the actual size of the input image. And it also has these characteristics, residual connections between layers of the same level of the U that allows us for a more stable training. Okay? And this type of network is used a lot, not only for segmentation, because imagine, no? The input is an image and the output is another image, so you can have the input image under labels, the input image under the noise version of that image, or the super resolve version of it, different channels, you can do peaks to peaks. There's a lot of possibilities for these networks. Even nowadays, now all the image generation from text, at some point they have something like this to produce the final images. And this is something that we can use for the semantic segmentation to get the object probabilities of our object of interest, in this case, mitochondria, could be anything else, at a pixel level, both in 2D and 3D. In 3D, the architecture is very similar, but the filters are in 3D and the downsampling as well. Okay, so we know now how to do the first step. What about the second step? No, okay. Something very intuitive would be, okay, if I have probabilities, I can just apply a threshold, binarize my objects, and then check all the connection between the pixels. No, so how do we do this? Again, we have very classic algorithms such as connected components that takes an image. Actually, if this is our input image, you have to invert it, because what it does is that it paints, let's say, every object in white with a different color, a different ID. So at the end, we have all the objects in the image with a different number. Here it's represented with a color map, so we can see it better. There are classic ways of doing this, and it's implemented in many libraries, in Python, in Java, etc. The only parameter that it has is this connectivity parameter, 4 or 8 in 2D and 6 or 26 in 3D. What is the meaning of this? Well, at the end, if we use 4 connectivity, for example, in 2D, we're only going to look at the direct neighbors of every voxel or pixel, sorry, in the top, down, left, and right position. So the corners are never considered as part of the same object, which is what we have if we check the 8 neighbors at the same time. In practical terms, if we use 4 connectivity in 2D or 6 connectivity in 3D, our final masks are usually more rounded than if we use the 8 or 26 connectivity. So generally, you want to use the 4 or 6 connectivity, because we tend to segment things that are more like potato-like structures, right? Okay, but this doesn't come without issues. This is very fast. We can do it right away. But of course, when we binarize, we may run up into problems, because the object probabilities are never perfect, and the threshold is usually hard to get. No, so we can get out of a probability like this different objects where one should be. So this is called a split, or we can merge objects where they should be different objects. Now this is called a merger. So the problem is that our results are going to be very sensitive to this binarization process. So can we do better? Yes, of course. We can also go for another classic algorithm, such as watershed. So just to refresh your memory, you probably use it, or you're familiar with the term. Watershed is this classic algorithm from the 80s that we still use a lot because it's very useful. It's quite fast. You take all the grayscale levels of your image and imagine that it was topographical surface, no? Where all the whitish pixels would be the mountains and the darker pixels would be the valleys of your surface. So what you do is that you identify the local minima in your image and then rise the water from each of those so-called basins. No? So you go iteratively rising a different water from every local minima. And when they touch each other, the waters from different minima touch each other, you put a border there, or what we call a dam in the watershed terminology. Okay? I usually put my students this image here. It's very nice. It's a confocal image where a fluorescence marker in a membrane marker. So you see that if you represent it in 3D, it's easy to imagine that you simulate the water coming up. At some point, they're going to touch each other in the highest peaks of this mountain chain-like structure, right? Again, it's not problem-free, because even you have very nice confocal images like this, where the input of your cells, they look very, very dark. They are never zero values. No, they have 7, 6, 3, 4 values. So there's a lot of local minima. And as I said, you have many local minima. Every of them is going to be considered one object. So you end up with over segmentations. Of course, this is something old. So they came up with a solution that is called marker control watershed, where you, instead of calculating local minima, you impose from which pixels or voxels you're going to run the watershed, the flooding. Okay? So you have hopefully the perfect markers for every object, one marker per object, you're going to end up with a perfect segmentation. How do we do this? We'll see next. So more or less, this would be a full pipeline for an instance segmentation. Now we know that we have 2 steps. In the first step, we have a full image. Then we have to make patches and pass all the patches through the network. And in the second step, when we have the object probabilities, we undo the patches. Now we create the mosaic of the entire image, and then we run the method for instance extraction. Still, this is the weakest point in our key chain, right? Because here, the problem is that if we don't have very good probabilities, meaning that this network didn't work super well, or the data was tough, then we have mergers and splits, and then the instances won't be good. Okay? We saw that, for example, in our MitoEM dataset, where we have mitochondria that suddenly went very thin in 3D, and then back again thick, thin, thick, and then those thin points are very hard to get, and then they basically screw the entire instance segmentation. So can we help the post-processing based on the model? Well, actually we can. No, this is from 2016, where there have been a lot of research on this. Already in 2018, they presented this nice approach where they said, okay, when I'm in such a situation, I know that solving splits or artifacts in the post-processing step is more or less easy, because splitting, even with proofreading splits, I just say, okay, no, this guy and this guy, they go together. And artifacts are usually dirt, no, and things that don't look really like the other objects, so we can remove them more or less with some filtering. But mergers are difficult, because, especially in 3D, because you have objects that are merged together, you have to decide where to cut them, and in 3D, the proofreading can be very painful. So these guys, they came up with a solution, and they said, okay, instead of only predicting the object probabilities, we're going to predict also the borders of the objects. Actually, they did that with some weights in the borders where they were touching other objects. Okay, so basically they use the same type of network, but now with two targets: object probabilities and boundaries. Okay, so they had to adapt the error function, the loss function that they use, but it works quite nicely. Actually, it works. It's what we call a multitask network because it does two things at the same time. It creates two things, and both are helping each other. No, when you calculate the borders, then the object probabilities also get better. So you can improve the results of the post-processing just by doing this. You can ask, can we still do better? Because I know that there's some methods there that do better than this. Of course, we can. No, the first people on working on this were the people from Stardust, and they said, okay, when I try to do segmentation, instant segmentation of images, the most common source of errors are these two: noisy images and also very crowded cells. Imagine this is a very nice example. You know, you have these three different instances. You use something like the unit. Well, it's tough to get the border here. So you may end up, even if you do this trick of predicting the boundaries, you may end up with merging everything into a single object. And if you use something like the mask RCNN that predicts the bounding boxes of every object, because all the overlapping boxes are measured in order to remove similar detections, you would end up probably with just one single object here. So what they did is, again, a multitask network. They said, okay, we're not going to only predict the object probabilities, but also what they call the radial distances. So they fix a number of rays from the center to the borders of the objects in a specific direction. For every direction, they have a new challenge as output. And then when you have the object probabilities and all that set of rays, then they do some post-processing to propose polygons for every object that match that configuration of rays and object probabilities. Okay? And then they do some non-maximum suppression also to remove polygons that are nearby. Okay? Let's see an example. No? This is a very characteristic image. It's noisy, plenty of objects touching each other. So what they do, the model does, and then, as you see, again, sorry, I didn't mention, but this is also a unit-like architecture. Okay, what they do is that they predict the object probabilities. In this case, is actually quite a good job because they separate things that are already touching, but it's not perfect. And also all the distances in a specific directions. Okay, the more distances, the more radian distances that you have, the more accurate is your boundary in the end, but of course you have to spend more time training. So out of that, in the post-processing step, they have what they call a convex polygon for every object, actually more than one usually. So they have to do some non-maximum suppression to get just the most likely one on every object. But it works very nicely. They also presented this to do it in 3D. So it's just a 3D unit-like architecture with the same type of outputs, no? The object probabilities and all the distances, but now in 3D. So they show that this is actually competitive with the mask RCNN, with many less parameters, but they also recognize the limitation, that is that it can only segment things that allow this ray representation, meaning that from the center you have to see the border. So it only segments things that are convex. Okay, and not all our segmented problems are convex-like. No? So this is what the people from CellPose said later. I said, okay, not all our cells that I need to segment, they are blob-like objects. So they came up with this other idea, where they simulate the diffusion process from the center of the cell towards the borders that can be represented with just spatial gradients in X and Y, okay? And actually, they very nicely represented it later with this, they call flow representation, no? They normalize the direction of the flows to the center with this very colorful image. And this is nice because with this representation, you can see actually adapt the whole thing to many different shapes, not only convex shapes. No, this is kind of another kind of distance representation, but it adapts to non-convex shapes as well. And they presented this again, a unit-like architecture, okay, that predicts three things: what they call the inside cell, but this is object probabilities, and then the horizontal flows and the vertical flows of the objects, okay, represented like this. Then in the post-processing, you calculate the flow field, and in order to assign every pixel to a different instance, what you have to do is follow the flow, and if it ends up in the same center, it belongs to the same instance, okay? And this is how they extract the instances. Moreover, these people, they wanted to do a generalist cellular segmentation model. And for that, they also trained on a very diverse data set, meaning different image modalities, but not also image modalities. They also put there some crowded scenes of, for example, fruits, rocks, objects that look a little bit like cells but are touching each other. So the network is used to see these crowded scenes, but with other type of objects. And for 3D, they said, okay, annotating in 3D is a pain. So let's just reuse the 2D network that we have trained and use it in the other two planes of my 3D data. This can be risky, as you know, especially because the resolution in Z is usually not as good as in X and Y, but you can compensate from that and then extract those gradients in X and Y on every plane, and then combine them together to get 3D flows that follow the same strategy, and then you get the 3D instances. Okay, so in BiaPy, we thought, okay, we can incorporate these kind of approaches to do something generic, so people can actually play with this, because again, we are also interested in developing new methods in the whole 2D or 3D pipeline. So the idea is that we want to use a unit-like architecture in 2D or 3D with multiple outputs. You know? For example, the object probabilities, the boundaries, and different distance representations of the pixels of the object to the boundaries, etc. And then this would help the post-processing. How? Well, let me show you a real example. This is from a paper that we have published very recently with some cyst segmentation in 3D. Well, I'm showing just one slice. What we do is that we predict on this channel the object probability. You see that it's not perfect, and this is just one slice, but you see that these guys probably should have not be connected, right? We also predict the boundaries between the cells, and then we predict the distance representation of it. It could be, for example, the regular distance to the borders, which is, again, is not perfect. You see that inside the cyst, in this case, there are some distant values that shouldn't be considered. But still, the representation is quite good in the cells. So if we want to use this with a regular marker control watershed, what we do is we first threshold our predictions and the object probability with a medium-high threshold. So we get the whole donut here, no? Which is all the area that we should consider. So we could use this to mask out the results to be considered as having cells. So we're going to forget about errors like this or like that here. Okay, so this is already good enough to mask our results. Then we can use to get the markers, which is the most important thing, because remember, we need one per object. Use a combination of a high probability here that would give us something like this, and a high threshold here too, to impose the borders in order to separate the touching markers when they don't have to be touching. Okay? So this could be our marker image. And then in the end, we need to run this watershed algorithm in something that looks like a topographical surface. If we use the distance image, we will have the distance to the border. So at the center of the object, we will have peaks And we said that we want to have valleys, so we can take something like the inverse of the distance. So we do this for our 3D confocal cyst images, and we get very nice final segmentations. How easy is this to be configured in BiaPy? Again, in the YAML file with the typical template, it's just a matter of changing the data representation of the problem. Okay, so in this case, this BC means binary. I think it's binary mask, no binary object class categories, and then C is for contours. But of course, you don't need to know that. Now, if you go, for example, to the example that we have in the notebook, we already have a nice menu, or in the GUI is the same, where you can go to the problem representation, and with natural language, you can understand better what is going on. You can select binary mask, contours, foreground mask, distance map, what kind of distance, etc. So just to sum up, I hope I convinced you that we have now quite ready to use all-in-one library for bioimage analysis workflows. Okay, they all use deep learning at its core. So hopefully you have a GPU, it's going to train faster. If you don't need to train, and you can apply it in CPU, that's fine. All the typical workflows that we have, and more that are coming, are defined by templates. We are providing notebooks. We have everything in a container, so it's hopefully easy to install. And that's why we say that it's oriented to all audiences. Hopefully for many inexperienced users, it could be also attractive. We have microscopy-specific solutions. Again, I show you that. And I want to remind you that we are under continuous development. So we have a quite interesting to-do list. And right now, we move everything into PyTorch. We started with Keras, but now Danny decided that it was better to run into the trend, which is PyTorch. So we have everything moved to PyTorch already, but we need to test it. So if you want to try it, I would be very happy. And we have to make a new stable release for it. We want to partner with the ImageSC forum, so we can redirect all the questions and doubts to the forum. Want to also integrate and partner with the bioimage model too. So again, answering one of the original questions, we would like to have pre-trained models already up there, or models from our own publications. We've been asked to create an Apari plugin, which I think is interesting for this part of the community. And I think the most important thing is that we need to increase our community, right? So both for users and developer numbers should increase in order for this to be successful. So that's it. I just want to acknowledge all my students that work in different parts of the library, past and former students. And also, this is the list of collaborators that we have right now using the library. So hopefully things will come up soon. And I would like to hear from you. So thank you very much for your attention.